Hello, everybody. Starting chapter 6. Let's get to it. 6.1, we want to talk about key features of our newest function, exponential. Key features of exponential functions. All right, so we're moving into the exponential stratosphere here. What we're going to do is the way we're going to interpret is we're really going to be looking at graphs, and we're going to help get some graphs by using tables, and ultimately we might look at a few equations here. All right, so example 1 is we're going to identify those key features. We want to know, what are we looking at? That's not how you spell features, but we want to know, based on a graph, what are some things that we can look for in an exponential? Okay, so best way to do that is by having a table. Get an idea of where points can go on a graph by using a table. So we'll make our little f of x table, and I'll come over here. I'll make a little graph. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So we're going to evaluate this function at -2, -1, 0, 1, and 2. Now, this function, look, right? We have an exponent, but instead of usually a number, now we have a variable in the position of our exponent. So that's why we call it an exponential, because it's a function that depends on the exponent. So we pronounce this as 2 to the power of x. More commonly, we say 2 to the x. 2 to the x. That's our function. So let's evaluate. If we plug in -2, we're going to get 2 to the -2 power, which if we do in our calculator gives us 0.25. And remember, guys, because I'll take it over here, remember, 2 to the -2 means we flip, when we have negative exponents, means we flip the fraction on its head and we make it positive. So now it's 1 over 2 to the positive 2, which is 1 over 4. So that's where 0.25 comes from. Bringing back exponents, you know. All right, so 2 to the -1 is going to be 1 over 2 to the 1, which is 1/2. If anything to the 0 power is 1, 2 to the first power is itself, 2 to the second power squared is 4. Okay, so let's get a glimpse of what we're looking at here. Let's go to -2. I'm going to be at 0.25. -1 up to a half-ish. At 0, we're going to be up here at 1. 1 over here at 2. And 2. Now we're up here at 4. And now we kind of really see this curve coming in, and we start to take off. We start to rocket off. And that's what we should expect when we see an exponential. And we call this a curve because we're no longer dealing with the lines, right? It's not a line. It grows exponentially, so it grows on a curve. All right, so let's talk about a couple things here. Let's talk about domain, range. Okay, so first of all, domain. Are there any values that we can't plug in for x? Let's think about it. If we plug in negative numbers, that's cool. If we plug in 0, that's cool. And if we plug in positive numbers, so we can choose anything we want for x. There doesn't seem to be any restrictions, and we have arrows in both directions. So we're going to use our symbol for all real numbers. All right, let's think about the range, the outputs. If we put in a negative number for x, will we get numbers back? Yes, we'll get fractions. If we put in 0, do we get a number? Yes. If we put in positive numbers, will we get a number out? Yes. So our range is not limited. There are no restrictions. Plus, you see the arrows tell us that it's all real numbers. Okay, certainly we can identify an intercept. We should be looking at it right here. There's our y-intercept, which is at 0, 1. And if you notice, we actually don't have an x-intercept. And this brings us to our next point. What we do have is an asymptote. Remember, guys, an asymptote is a line that a graph approaches and gets really, really close to, but it never touches. And here's why. Let's go back to this example. Guys, pick a number like -5. 2 to the -5. You flip it on its head. It's 1 over 2 to the 5th, which is 1/32. In your calculator, guys, 1/32 is 0.03125. That means even if you put in really, really small negative numbers like -100, you're still going to get 1 over some number, and you're always going to get a fraction. you're never going to actually get to 0. Because 1 over something, even if it's a huge denominator, is always something. It's itty bitty, but it's always something. It's not going to be 0. So that's our deal, is that we have an asymptote that the curve flattens out and it approaches, but will never touch 0. Okay? Lastly, we want to talk about our end behavior. So as x approaches negative infinity, meaning it goes to the left, so we're thinking over here, as x goes to the left, well, we just talked about it. What does our function do? It gets closer and closer to 0. It approaches 0. And on the other side, as x approaches positive infinity, goes to the right. Think about numbers like 5, 10, 25, 100, all those big numbers. As our graph goes to the right, what's happening? The graph is skyrocketing upwards. So our function is going up and up forever, so it's approaching positive infinity. So these are some key features that you'll see here. Unrestricted domain, unrestricted range. It's a curve that to the left goes down towards 0, to the right it skyrockets up forever, and there's going to be some y-intercept that hits, because anything to the 0 power is just 1. Okay, so we'll drink that in for a second. We'll get a little vocab down here real quick. An exponential function. Pretty straightforward. In general, it is in the form y equals a times b to the x, where a is usually thought of as our starting value, and b we typically call our growth factor. What is being operated on exponentially? Okay, there's a couple things. Stuff can't grow if you don't have anything to start with. So a can't be 0, and b has to be greater than 0, but it also can't be 1, because if you're growing things by 1, if you're multiplying 1 over and over and over and over, right? When you multiply 1 over and over and over, you just get 1. So there's no change. Okay. So with that in mind, we'll build on that, but let's just do a second example here to get a different feel. So g of x is 5 times 1/2 to the x power. Once again, it's an exponential because our variable is in the exponent position, so that's how we can recognize that. Let's make ourselves a little table. Get a feel. -2, -1, 0, 1, 2. Give ourselves a graph. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 6, 7, 8, 9, 10. All right, I'll go up to 10 and you'll see why. All right, let's do it. So honestly, in our calculators, we can do 5 parentheses 1/2 to the -2. And we get 20. 5 parentheses 1/2 to the -1. We get 10. Anything to the 0 power is 1. So 1/2 to the 0 is 1 times 5 gives us 5. Then we can do 5 parentheses 1/2 to the 1, which is 2.5. And then lastly, 5 parentheses 1/2 to the 2 is 1.25. Now, hopefully we notice that our pattern is now, as our x values increase, we're getting 20 down to 10, down to 5, down to 2.5, down to 1.25. And I want you guys to think about where in this equation, why you think that might make sense, that we're actually losing money, we're losing value exponentially. So we don't need to graph 20 because it goes off the graph. So let's go to -1, 10. Let's go to 0, 5, 1, 2.5, and 2, 1.25. And look at this. You now start to see, and it's pretty cool how it starts to happen. You now start to see this curve taking shape. And just trust me on this, where I'm going to curve it out, and I'm going to kind of level that curve out. All right, so let's talk about a couple things again. Domain and range. Domain, can we plug in anything we want for x? Sure, we can choose whatever we want. There's no restrictions. Our arrows go both directions, so it's all good. All real numbers. What about our range? So once again, can we raise 1/2 to negative numbers? Yes. and we'll get outputs. Can we raise it to 0? Yes. Can we raise it to positive numbers? Yes. Once again, we have both arrows on our graph, so we get all real numbers, no restrictions. Okay, let's look at our intercepts again. So we have a little different intercept. Our y-intercept is now at 0, 5. And I know when you plug in 0 for x, you always get anything to the 0 power is 1. But look at our starting value. We actually started with 5. So even though when you raise it to the 0, it becomes 1, now our starting value, our y-intercept, because of that 5 in front, is actually now at 0, 5. And once again, the reason that we rounded out this function is because there is an asymptote at y equals 0. Because if you raise 1/2 to the 50th power, no, let's not do that. That's crazy. Let's raise it to the 7th power. You get 0.0078125 times 5 gives us some small fraction. But again, you're always going to get a small fraction. 1/2 multiplied repeatedly, you're never going to get 0 because you always are multiplying. You're going to just get really, really small fractions. So once again, we are approaching x equals 0. So let's see how the end behavior kind of changes a little bit. So as x approaches negative infinity, so as our x values go to the left, let's look as we go this way to the left. What's our function doing? It's pointing straight up at the sky. So our function g of x approaches big, big, big numbers, positive infinity. And then as x approaches positive infinity and goes to the right, goes over here to the right, look what it's doing. It's bottoming out, it's flattening out, and it's sitting down right almost on top of the line y equals 0, but not quite. So we say it approaches 0. Okay, and here's the big two things I want to emphasize here, is I want you to look at the difference in the f of x function and the g of x function. Ready? F of x function, there was no starting value out in front. Remember this starting value? There was no starting value out in front. So when we plugged in 0, anything to the 0 power is 1. Hence why our starting value here, the y-intercept, was at 1. Secondly, look at the number that's being raised to the exponent. It's a 2. When you raise numbers like 2, 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16. Now you start skyrocketing as you plug in bigger numbers for x. Hence why our function curves and goes increasing as we go to the right. Alternatively, look at our g of x function. Our starting value was 5. So when you raise something to the 0 power, it's 1, but times 5. This is why our new starting value, our y-intercept, was at 5. And the other thing is that look at our growth factor. It's 1/2. So we still call it a growth factor, but actually it's decaying. 1/2 multiplied repeatedly gets you smaller and smaller and smaller numbers. So as we plug in numbers like 2 and 3 and 4, 1/2 to the 2nd power and the 3rd power and the 4th power gets smaller and smaller and smaller. So our curve acts kind of in the other direction and goes downwards, curving downwards as we go to the right. So that we're going to build on those two things, the idea of the starting values and the growth factors. But for now, give this triad a shot. Give yourself a table, see what you're looking at, see if you can identify the key features.